Today we are going to discuss this vapor liquid equilibrium. So the plan is first we will introduce this general vapor liquid equilibrium or VLE relation, and from there we will reduce it to modified Raoult's law and subsequently to Raoult's law. And next, based on that, we will try to understand this PXY and TXY diagram, and in the next session probably we will move on to solving different standard VLE problems, which will be followed by flash calculation. So you see that vapor liquid equilibrium abbreviated as VLE, the relation actually originates from the condition of phase equilibria, right. So whenever these two phases are in equilibrium, and it's a multi-component system with two phases, alpha and beta, and here it is liquid and vapor. So the fugacity of all component species in liquid phase will be individually equal to the fugacity of the same component species in vapor phase. So that's basically the condition which actually evolves out from the equality of partial molar Gibbs energy, that is the chemical potential, and from there we conclude that the fugacity, which we have demonstrated previously, that fugacity of these two phases for individual components must be same, and that is the component species fugacity. So Fi cap V will be equal to Fi cap L, right. So we have discussed this actually, but again we are repeating it because we are now going to focus specifically on this VLE. So for vapor phase, Fi cap V is equal to Yi into P into phi I cap. So you know how to solve for this phi I cap using at least this virial equation, and from there the mixing rule of the second virial coefficient, we have discussed it, right. So though there are different other techniques for solving this phi I cap using cubic equation of state for this mixed gas phase or the vapor phase, but we have for the GET it's not exactly mandatory, so we have skipped that, but still we know that how to solve for this phi I cap using this virial equation, right. Now for liquid phase, Fi cap L is equal to this gamma I xi Fi naught, right, which will be gamma I xi into Fi considering simple solution, because non-simple solution, that vapor liquid equilibrium is beyond our scope, and Fi, this fugacity of a pure liquid species, it may be at high pressure, right. Why at high pressure? Because the VLE we may be discussing at a different pressure relative to its saturation pressure. So we have to include this pointing factor. So it is gamma I xi phi I sat pi sat into Pf, where Pf, the pointing factor, is equal to exponential of VIL pi sat P minus pi sat by RT. So necessarily, if I write the expressions, we will get Yi into P into phi I cap is equal to gamma I xi phi I sat into pi sat into Pf. So that's further, the form may be further compressed upon introducing this capital phi I, which is gamma I xi into pi sat into Pf, where capital phi I is defined as, you can understand this phi I cap by phi I sat. Right. So it's in the order of 1. Order of, I'm not saying it's exactly equal to 1. So this is the general VLE relation. General VLE relation which is universally valid. So this is the general VLE relation and that's universally valid. Now for low to moderate pressure, there is pressure less than 10 bar, we have capital phi I, as I mentioned, it is in the order of 1, it is close to 1 and also pointing factor can be approximated fairly close to 1. So we have yi into p is equal to gamma I into xi into pi sat, and that's known as modified Raoult's law. Right? Further, so in the modified Raoult's law paradigm, you can understand the liquid phase is considered non-ideal, whereas the vapor phase is ideal, because this must be supposed to be the vapor phase fugacity, which is equal to partial pressure, and we know that when fugacity is same as partial pressure, it's nothing but the ideal gas mixture. So vapor phase is ideal. However, liquid is a non-ideal solution. A liquid phase is a non-ideal solution. Right? So that's quite rational for low to moderate pressure, that is up to 10 bar. Further, now there is the for ideal cases where the vapor phase is ideal, the liquid phase is also ideal. So this is ideal liquid phase, then gamma I equal to 1 and we have yi into p is equal to xi into pi sat, and that's typically the Raoult's law. Right. So you see, if I look into the structure of these two, we can conclude that if gamma I is greater than 1, and on this side what we have, this is equal to partial pressure Pi, right, and this is also equal to partial pressure. So partial pressure predicted by Raoult's law is equal to xi pi sat. Let's call it pi r. R stands for Raoult's law, right, and here it is gamma I into xi into pi sat, so it is gamma I into pi r. Okay. So basically, if gamma I is equal to 1, pi is greater than pi r. So pressure, partial pressure is greater than that predicted by Raoult's law. So in that case, it's referred as positive deviation, cases of positive deviation from Raoult's law. So if gamma I is greater than 1, it is a case of positive deviation from Raoult's law. and second, if gamma is less than 1, it is a case of negative deviation from Raoult's law. That is, here Pi, the partial pressure, is less than PIR, and here this is Pi is greater than PIR. So that's the relation for VLE we are looking for, and now we are going to understand the very basics of this pictorial representation of VLE, that is the PXY and TXY diagram. So primarily we will discuss this TXY diagram, and next we will move on to more fundamental PXY diagram. Right. So this data, it's a outcome of VLE experiment. For different system we can conduct it, and what is that? TXY diagram of vapor liquid mixture. Now definitely it is a binary system, right? So liquid phase mole fraction of more volatile or high boiling component is X. So definitely X1 is equal to X and X2 is equal to 1 minus X, and for vapor phase mole fraction of more volatile or high boiling component is Y. So Y1 is equal to Y, Y2 equal to 1 minus Y. Right. Now feed composition is Z. There is a mole fraction of high volatile component is Z, that is Z1 is equal to Z, Z2 equal to 1 minus Z. Now what we do in general? See, for TXY diagram, fix the pressure at P, right? Okay. And what you have to do, you take different mole fraction solutions of the feed, that is you go on changing Z for different set of experiment, or you can actually generate this partially if you fix this Z and go on changing T. Okay, that can also be done. So anyway, conducting VLE experiment at either at different X or different Z or at different T, we generate VLE data in the form of TXY, right? So, you record the temperature, measure the mole fraction of the liquid, and will also measure the mole fraction of the vapor. So, if now we plot it, right. So, we will get, say, if I have conducted a specific Z, say we have conducted a specific Z. So, this may be the liquid phase composition, this may be the vapor phase composition. Vapor phase will be rich in more volatile component, while the liquid phase will be rich in less volatile component, and this is T, right? Pressure is fixed. Now, if I change the temperature a bit, provided the two phases exist, we can again generate, or we generate this at here. So, it will split again into X and Y, right? Or we can go on changing Z and keep the temperature fixed, and from there we can also generate the different data points. So, now if I join them by a smooth curve, I will get, sorry, I will get this sort of curve, right. Okay, let me draw it in black ink. I will get this sort of curve. So, the fact is, there are two different lines. So, this represents the liquid phase composition, the locus of the liquid phase composition upon changing temperature. So, this is T versus X, and this is T versus Y. Now, why they meet at X is equal to 0 and at X equal to 1? Because X equal to 0 represents pure 2. So, it has got a fixed boiling point, right. So, let us call it T2 sat, saturation temperature, or the boiling point at that specific pressure. And here X equal to 1 means pure 1. So, we are getting T1 sat. And intermediately, we are generating these horizontal lines, and this horizontal line, you see, it connects the two phase compositions in equilibrium, and from this stoichiometry we know that this is called the tie line, right. This is the tie line, and if this is Z, let us say the point is P, this point is A, and this point is B. Simply by a balance, we can write that F, which is the amount of feed, is equal to amount of vapor formed and amount of liquid formed, right. So, this is the overall material balance. And F into Z is equal to V into Y plus L into X, that is a component balance for a binary system. Okay. Now, you see that if I replace this V plus L here as F, V into Y plus L into X, then L Z minus X is equal to V Y minus Z. So, L by V is basically Y minus Z divided by Z minus X. And from here you see this gap is basically Y minus Z, and this is basically Z minus X. which is equal to the line segment AP divided by PB, right. So, AP line segment length divided by PB line segment length. Okay. So, you see its L is on this side, it's proportional to AP, V is on this side, it's proportional to BP. So, it's just like the moment balance in a lever, right, the lever of class 1, and that's called the lever, and that's this rule is called lever arm rule, right. It's not only valid for vapor liquid equilibrium, but for any phase equilibrium, right, where we know the composition of the feed and how it is distributed in the two phases. So, from this lever arm rule, knowing y, x and z, we can actually get the ratio, and we know how much amount of feed we have given, and from there we can calculate online that what is the amount of vapor formed and what is the amount of liquid formed. Definitely it needs a bit trial and error, right. So, here we have got this understanding of the lever arm rule and a tie line and the equilibrium between the two phases. Now, you think that there are actually in this graph, okay, let me draw the graph once again. So, graph from this x or y between 0 to 1 will be moving downward, right. It may be having an intermediate maxima, right, but it will be moving downward. Why? Because the T1 sat, which is the high boiling component, must have a lower boiling point compared to T2 sat, which is a low boiling component. So, there are additionally, there are 5 different thermal phases possible. So, for a given Z, you see when it is we are here, when we are here, this is state 1. So, state 1 stands for subcooled liquid, right. State 2, when the first drop or first bubble of vapor appears, right. Because at this point here, once we are here, there is a liquid and here it is just saturated. So, we will have a vapor which is in equilibrium with this same Z, right, and this will be the composition of the first bubble of vapor which is appearing in that system, and 2 is basically this thermal state, that is saturated liquid. And as the first bubble of vapor appears at this point 2, T versus X line is alternatively called bubble curve, bubble point curve. Right? Next you go on to here, phase 3, state 3. So, it will split into 2 phases with a relative separation of the 2 components upon vaporization, and the same principle we actually explored in the process of distillation, right. Because the vapor phase, we are getting this understanding, it will be rich in more volatile component, whereas the liquid phase is rich in less volatile component. So, the phase 3 is 2 phase. Now, as you go on increasing the temperature, you will eventually reach a state 4 where the liquid vanishes, right. So, state 4 is a saturated vapor. And the state 5 necessarily it is the superheated vapor. So, this is the vapor phase, this is the liquid plus vapor, this is liquid phase, and the lines represents the saturated and saturated vapor and saturated liquid. Now, similar to bubble point, if we go from, or if we think this changing of thermal state in a reverse direction. Let's say I have a superheated vapor and I go on reducing its temperature. So there will be a point where the vapor is just saturated and the first drop of dew will appear, right? So the dew will have a composition here, right? Because this is the vapor phase, this is the liquid phase, the dew is getting formed and it has got a composition same as this point. So similar to the bubble point curve, this T versus Y plot is alternatively referred as dew point curve. Right? So T versus Y is alternatively referred as dew point curve. So that's all about the TXY plot. Okay. So it's given, or it is basically being generated at a given pressure. Now additionally, there is another point to be noted, that if we go on increasing or changing the pressure in general, what will happen? Definitely with a change of pressure, T1 sat and T2 sat both will go on increasing, right? And there will be a point where we cannot separate the liquid phase from vapor phase, because we have already reached the critical point of component 1, right? So you see, at a very low pressure, the curve is something like this. Its two-phase region is quite bludged out. So at higher pressure, the two-phase region shrinks. Now, so this is at P1, this is at P2. Next, say we have reached the critical pressure of component 1. So what will happen? The derivative discontinuity, here we have a point of derivative discontinuity. The derivative discontinuity will be maintained at x is equal to 0. However, here it will be a smooth curve, that means it is at the verge of separation. See what happens. It will be narrowed down, definitely, right. So P3 is equal to P1 sat. Now further, if we increase the pressure, so this point will separate out from x is equal to 1. But still this side is attached. So here the P4 is greater than P1 sat, but it is less than P2 sat. Right. However, if we move above and over, so at P4 is equal to P2 sat, here we will have a derivative continuation. The derivative of this curve will no longer be discontinuous from one arm to another arm. However, at still higher pressure, we will have the two phase surviving over some intermediate region, right. So here P is greater than P1 sat and P2 sat as well. Now you see, so this is temperature, this is x or y. So this P1 is less than P2, less than P1 sat, less than P4, less than P2 sat. So that's the hierarchy. So if I think of a feed of composition Z, so here we have this as y1, this as x1. The same feed at same intermediate point with an elevated pressure, naturally the temperature will increase. So you see that this is y2, this is x2. Further it will decrease also. right. So, it will go on reducing the two phase, the gap between. So, we can write this yi minus xi, that mod is decreasing, or yi minus xi, yi is naturally greater than xi, always decreases with increasing pressure. Right. So, separability actually, y at the gap actually represents quantitatively what is the separability of that system at definite pressure. So, if we go on increasing the pressure, we can understand the separability upon vaporization, right, partial vaporization, that decreases. Okay. So, we should always conduct a distillation preferably, if we do not think of economy, at a lower and lower pressure. Okay. And that is why you see that when we fail to separate the components from a multi-component mixture such as petroleum, any further in atmospheric pressure, we jump to vacuum distillation units. So, that is why the reduced crude oil from the bottom or the bottom residue of this atmospheric distillation unit in petroleum refinery, it is further separated into lube oil feedstocks like gas oil, the spindle oil, intermediate oil, heavy oil, etc. Right. This can be serving as a lube oil feedstock and alternatively the feedstock for the secondary refining. We know that this can be further catalytically cracked or thermally cracked to generate the more valuable products like gasoline or diesel. Okay. So, we have to note that distillation technically is always favored at lower pressure. Right. So, that is the idea of Txy plot. So, with this understanding of this Txy plot, let us move on to Pxy plot, which is more fundamental from the perspective of this quantitative VLE relation. So, you see this Pxy diagram of vapor liquid equilibrium system. Temperature is fixed. So, the same technique is being applied and we generate the Pxy plot. Now, if we just try to think theoretically, what will be the nature of the curve, right? In real life, this two component mixture. So, definitely when x is equal to 1, the pressure will be the saturation pressure of component 1, and as component 1, and similar is for x equal to 0, where the curve should merge, the two curves should merge at P2 sat. So, P1 sat will be obviously higher than P2 sat. Why? Because component 1 is more volatile. So, at a given temperature it must exhibit higher vapor pressure. So, above and over P1 sat, for if I think of pure component 1, here what we will have? We will have pure vapor phase, superheated vapor phase, and here we will have subcooled liquid phase, right? This is basically the boiling taking place. So, once we move into the space of this phase diagram, so from the point it will enlarge just like Txy plot. So, the nature of the curve will be something like this. Right. Just the reverse in terms of its slope compared to this Txy plot. So, this is vapor phase, this is liquid phase, this is vapor plus liquid phase. So, if I have any feed, it will split into two, right. sorry, this is vapor phase, this is just I have missed this is liquid phase, because when the pressure is here, it is I have mentioned that this will be the, when the pressure is higher, then definitely it is liquid. Just previously I was stating something wrong. It is obvious that here, when it is here for the component 1, then it will be vapor, right, and once it is here, then it will be liquid. So this is liquid phase, this is vapor phase, this is vapor plus liquid, and here this is y, this is x, and that is the typical tie line. So again, 5 different thermal states are possible. So if I think here, this is subcooled liquid, this is saturated liquid, this is two phase, this is saturated vapor, and this is superheated vapor, right. So 1 subcooled liquid, 2 saturated vapor, sorry, subcooled liquid, saturated liquid, then 3 two phase, 4 saturated vapor, and 5 superheated vapor. And naturally, this is the P versus X plot, which is the bubble point curve, and this is P versus Y plot, that is the dew point curve, right. So that is the basic idea of PXY plot. But why I am saying more fundamental from the perspective of qualitative analysis, from here we can understand the positive deviation and negative deviation. We will try to understand the positive deviation and negative deviation from Raoult's law. From this PXY, considering this PXY diagram. So you see that if I think of constructing this, Raoult's law, then we know for a binary system that y1 into p, which is equal to p1, is equal to x1 into gamma 1, x1 into p1 sat, right, which is p1r. So and for component 2, y2 into p, that is equal to p2, that is x2 into p2 sat, that is equal to p2r. So if I add these two equations, I will get p is equal to p1 sat into x plus p2 sat into 1 minus x, because x1 equal to x. So p versus x curve for Raoult's law, it is linear, right, and x equal to 0, if we substitute x equal to 0 here, then I will get this p2 sat, and x equal to 1, I will get p equal to p1 sat, which is exactly consistent with what we have just drawn. So, or it will be better if I use this. Or rather, let us use a solid line. So this is pressure predicted by Raoult's law versus x, right. It is a straight line connecting the 2 points at x equal to 0 and x equal to 1. Now, you see that P1R has got a linear relation, that P1R it's equal to what? P1 sat into x, P2R is equal to P2 sat into 1 minus x. So, obviously, if I connect this 0, so this becomes P1R versus x, and this line is P2R versus x, right. Now, regarding this plot for P Raoults versus y, so what we will do? x1 is equal to y into P divided by P1 sat, x2 is equal to 1 minus y into P divided by P2 sat. So, P within bracket y by P1 sat plus 1 minus y divided by P2 sat must be equal to 1. So, P is related to y non-linearly like this. So, it is a non-linear curve. Okay. So, it will be something like this, something like this. So, this line represents P Raoult versus y. Okay. Now, let us say we have a positive deviation, gamma greater than 1. So, P1 is greater than P1R. So, we will have this line as P1 versus x, and this line as P2 versus x. Now, question is why this curve is deviant from here and it is merging with the P1R when we have this x respectively, this x1 or x2. Here x1 is tending to 1, so it is merging with this Raoult's law, the ideal curve, and here x2 equal to 1 in this direction. So, it is also merging with this ideal curve, right. So, this is x equal to 0, this is x equal to 1. So, you can alternatively write this the direction of x1 and this will be the direction of x2, right, because this x equal to 0 means x1 equal to 0, here also x1 equal to 1, and this is x2 is equal to 1 and this is x2 equal to 0. So, it is the reverse direction. Now, you try to understand that we already know that when xi equal to 1, gamma I equal to 1, so it is ideal, right, and d gamma I dxi, we have proved it, d gamma I dxi at xi equal to 1 is equal to 0. So, the slope rate of change of gamma with xi is 0, there is no change. So, it is approaching the value of 1 upon merging with the ideal curve. So, that is the trend for P1 when it's the curve is not like this. Okay. So, it has got the highest divergence and when x equal to 0, because x1 is equal to 0 means it is an infinite dilution property of gamma, gamma is not equal to 1. However, when x1 tends to 1, gamma 1 is also tending to 1 and moreover d gamma 1 dx1 tends to 1. So, it will be merging slowly with the ideal curve for x1 and similarly for x2 because x2 is in this direction. So, this is the positive deviation from Raoult's law, and if I have positive deviation, you see, then x1 into P1 sat into gamma 1 is equal to y1 into P, and x2 into P2 sat into gamma 2 is equal to y2 into p. So, p is equal to x gamma 1 p1 sat plus 1 minus x into gamma 2 into p2 sat. Now, here p is a nonlinear function of x because gamma 1 and gamma 2 are nonlinear with x. So, we will have the curve like this. This is p, actual p versus x, and for y, the same technique we can apply, that p is equal to 1 divided by this y divided by gamma 1 p1 sat plus 1 minus y divided by gamma 2 p2 sat. Right. So, it is also nonlinear with y. So, p versus y, right. So, that is the overall representation of positive deviation, and you see we can think of systems like tetrahydrofuran and carbon tetrachloride. Tetrahydrofuran 1 and carbon tetrachloride 2, that is this component tetrahydrofuran, yes, or we can plus CCl4. So, it shows positive deviation, strong positive deviation from Raoult's law. Next is the negative deviation when gamma is less than 1. When gamma is less than 1, you see I am drawing it side by. Actually, I should have drawn it with in the same curve. So, x equal to 0, x equal to 1, this is p1 sat, this is p2 sat, and that is the curve for p versus p Raoult, p Raoult versus x, this is p1 Raoult versus x 1 or x, whatever, the same. This is p2 Raoult versus x, right, and this is, let us say it is p versus p Raoult versus y. Okay. Now, we have negative deviation. So, this one is p1 versus x, this is p2 versus x. So, we will have this maybe as p versus x, and this may be for p versus y. So, p versus x and p versus y. So, it will move downward. Okay. And the example is chloroform and tetrahydrofuran. Chloroform 1, tetrahydrofuran 2. Right. Chloroform and tetrahydrofuran, that is CHCl3 and this. So, that is the positive deviation and negative deviation. Now, what are the extreme forms of this positive deviation and negative deviation. It may happen that this curve P versus x will move up and off, P versus y will also move up, and P versus x and P versus y may touch each other at a certain point, right. So, we will be discussing the extreme case of positive deviation first. So, this is P versus x, this is P versus y, right, and at this point x is equal to y. So, this is x equal to 0, x equal to 1, x or y, and this is P, this is P1 sat, this is P2 sat. So, obviously, the respective Txy plot, if we generate for the same system, we will see that the curve looks like this. Okay. So, positive deviation, extreme positive deviation from Raoult's law give rise to minimum Bolling agiotrope. So, the temperature decreases. So, here this condition where x1 is equal to y1 or x is equal to y, that is referred as agiotropic condition, or alternatively we will refer it as minimum Bolling agiotrope. We can also have maximum Bolling agiotrope when we will have extreme, we will discuss these extreme cases of negative deviation. So, for extreme positive deviation or high positive deviation, we will have minimum Bolling agiotrope. Right? Agiotrope means where vapor and liquid phases have same composition. Right. Now, you see that this is T, this is x or y, this is T1 sat, this is T2 sat. Now, in an agiotropic system, or the example may be this furan plus CCl4. Furan plus carbon tetrachloride. So, furan is actually this. So, you see, if I am separating this, the furan and carbon tetrachloride by distillation, and I have given a feed here less than agiotropic, this is x1 Az, right. So, less than the, see here in this case we have Z less than x1 Az. So, vapor phase will be rich in high Bolling component, liquid phase will be rich in low Bolling component, it is fine. But here the liquid phase will be rich in low Bolling component, whereas the vapor phase is rich in high Bolling component, which is just getting inverted because of this agiotropic composition, right. But definitely this is an absurd case, we don't have rather this feed with composition above and over agiotropic composition, right. So, if it is being fed, we will see later in mass transfer that if it is this feed is being fed to a distillation unit, continuous multi-stage distillation unit, and if let us suppose we can achieve infinite separability upon introducing infinite number of stages in this distillation column, as a top product we will have the agiotrope, as a bottom product we will have the pure component too. Whereas here, if I give it here feed, though it is a theoretically possible condition, I will have this product, these two products, one will be the pure one, another will be the agiotrope. Okay. So that's the idea of minimum boiling agiotrope. Similar to minimum boiling agiotrope, we can have the extreme cases of negative deviation. Leading to maximum boiling agiotrope. Right. So what will be that? Again, this is the PXY plot. I will have here P1 sat, here it is P2 sat. So this is the extreme case of this negative deviation, and this is the agiotropic composition. Right, just the reverse as this will happen here, and respective TXY plot, this is P and this is T, X or Y, we are plotting it. So this is T1 sat, now this is T2 sat. So it is X1 AZ, just the reverse as this will happen now. So this is the maximum boiling agiotrope. Right. Now this example of extreme negative deviation leading to maximum boiling agiotrope, the system is ethanol and toluene. Ethanol 1, toluene 2, right. So point is, whatever it is, whether it is a maximum boiling or minimum boiling agiotrope, how to determine the agiotropic composition, right, because this is very, very important to know when we are designing a distillation column, right. We must be aware that whether it is going to give us an agiotrope or not. So determination of agiotropic composition, that is X1 AZ, which is same as Y1 AZ. You see that X1, if we apply modified Raoult's law, Y1 into P is equal to gamma 1 X1 P1 sat, and Y2 into P is equal to gamma 2 X2 P2 sat. Right. So as Y1 is equal to X1, P is equal to gamma 1 P1 sat, and here Y2 is equal to X2, P is equal to gamma 2 P2 sat. So gamma 1 P1 sat must be is equal to gamma 2 P2 sat at agiotropic condition, right. Now from excess Gibbs energy model, we know what are the expressions for gamma 1 and gamma 2 in terms of x1 and x2. Just like for the simplest example, ln gamma 1 is equal to ax2 square. So gamma 1 is equal to exponential of ax2 square, and ln gamma 2 is equal to ax1 square. Gamma 1 is equal to exponential of ax1 square according to 2 suffix Margulies model. So P1 sat by P2 sat is equal to gamma 2 by gamma 1, right. P1 sat by P2 sat equal to gamma 2 by gamma 1. So e to the power ax1 square divided by e to the power ax2 square. So e to the power a x2 x1 square minus x2 square, x1 square minus x2 square. So which is x1 plus x2, that's equal to 1 into x1 minus x2. So that is e to the power a into here x1 is x, x2 is 1 minus x. So it is 2x minus 1. Right. So ln of P1 sat by P2 sat, that is a into 2x plus 1, right, that divided by 1 by a plus 1 whole divided by half, it's equal to x1, is it? I think it's correct, right? Ln of P1 sat by P2 sat, a into 2x minus 1, a into 2x minus 1, okay. So that divided by a plus 1 into half equal to x1, is it? So that's the way we can find out the agiotropic composition. And thing is that it is a common understanding from the numericals that though P1 sat and P2 sat are strong functions of temperature, right, the strong functions of temperature, but the ratio of P1 sat and P2 sat is a weak function of temperature. So agiotropic composition is nearly universal, right? It's nearly independent of temperature for a given binary system, and that can also be extended to multi-component. Now here, in relation to this agiotrope and all, if I have to check the separability of a binary system upon vaporization, we must focus on a very well known quantity, as of all of you know, that is relative volatility. Relative volatility of component 1 with respect to component 2, this we are simply restricting ourselves within this two component system. So it's y1 by x1 divided by y2 by x2. This is the definition. So from there we can write that this is gamma 1 P1 sat by P divided by gamma 2 P2 sat by P. So P cancels out. So alpha 1 2 is equal to gamma 1 P1 sat divided by gamma 2 P2 sat. Right? So it's a function of what? x1, x2 and temperature. So alpha go on changing with liquid phase composition and temperature. However, the fact is that if I think, see, we have solved many mass transfer problem in semester where alpha for a given, where we have to draw this Markup-Thiele stage wise construction and all, it's given alpha equal to 2, right. So how come alpha is a constant? If I've got this equation, again the condition is P1 sat, this if we follow in Raoult's law paradigm, it's equal to simply P1 sat by P2 sat in Raoult's law. So in Raoult's law paradigm, this is nearly a constant. It is independent of temperature and there is no composition term. However, here the composition will be present, and that's why based on the change of gamma and that is a non-ideality, we can have different types of this y versus x plot. And note that here one is very important, as we have probably studied in mass transfer, that from this txy plot specifically we can construct this y versus x plot right. This txy plot is given like this, right, t x or y 0 and 1. So, simply we can construct this y versus x, 0 1 here x 0 1, upon drawing a 45-degree line, and for a given t, see, this is y, this is x. So, I will get the plot here, right, and at this point here it will merge, here also it will merge. So, I can construct a curve like this. So, here this curve is for Raoult's law paradigm, where we have a relation y is equal to this alpha x divided by 1 plus alpha minus 1 into x, where alpha is constant. So, this sort of curve may result, right. However, if this alpha go on changing with x1 and x2, we can have this sort of curve with a having point of inflection, this sort of curve, and we can have also this sort of curve, irregular, right, where that depends on what is the functionality of this gamma 1 and gamma 2, which is appropriate for this system. It may not be this 2 suffix Margulies model, it may be a Wilson equation, it may be NRTL, right, where this nature of the curve is too complicated. But if it is an ideal system, then alpha 1 2 is nearly constant, and we will have a relation y is equal to alpha x divided by 1 plus alpha minus 1 into x, which is purely a convex type of relation. Okay. So, that is all about this basic understanding of this VLE in relation to this Pxy, Txy plot, and subsequently we have studied these positive and negative deviations from Raoult's law, the extreme cases of positive and negative deviation. The extreme positive deviation may give rise to minimum Barling agiotrope, whereas the extreme negative deviation give rise to maximum Barling agiotrope, and in relation to that, how to find out the agiotropic condition, this relative volatility, and for feasibility check, feasibility checking of a distillation process, we have to set the condition of alpha 1 2 much greater than 1. It is pretty obvious, otherwise we cannot separate, and when alpha is close to 1, it has got a very low separability, or maybe it is leading to an agiotropic condition. So, that is all about the basic discussion of VLE. In the next session, we are going to solve the 4 different types of VLE problem. Thank you.